Well, guys, welcome to the remediation for the electron structures unit. You're watching this video because you need some more time and more opportunity to figure out how to draw orbital filling diagrams and also how to do Lewis dot structures. So that's going to be the focus of this video. By the end of today, by the end of this time, you should be able to draw both Lewis dot and orbital filling diagrams, both for ions and for neutral atoms. In order to get started, you're going to need your periodic table, and then if you have not already labeled it with the energy levels and sublevels, you'll need a pen that will allow you to do that. In addition to that, you'll need note-taking materials, because in order to get into the PRIDE review, you will need to have your notes from this experience. And then in addition to that, on our website where you found the link to this video, you will also find a link to a practice assignment that has 5 orbital filling and 5 Lewis dot structures, and you will need to print and complete that before you're welcome to the review session as well. So in order to get started, what we're going to do is we're going to help you step through labeling your periodic table. So if you grab your periodic tables and the pen or pencil that you're going to use to write on there, grab your periodic tables, and you'll notice in red that we've already labeled the periodic table just as we did in class. And so what you're going to need to do is down the left-hand side, you're going to need to label the energy levels on your periodic table, which range from 1 to 7. Then after you're done with that, you need to label the S sublevel, which you'll notice is 2 boxes wide, representing the 2 electrons in the S. That's on the far left. Then you'll need to label the P sublevel, which is on the right, and you'll notice that it is 6 boxes wide, indicating that there are 6 electrons in the P. Then finally, you're going to need, well, not finally, next you're going to need to label the D sublevel, which is the saddle of the periodic table. But notice that we labeled it D-1. You'll find out later that's because there's some overlap that takes place. And then finally, down at the bottom, you need to label the F sublevel. Again, that's 14 boxes wide because there are 14 electrons in the F sublevel. Then finally, the last thing you need to do in order to be ready is you'll notice that helium is a noble gas, but it actually is full at the end of the first energy level, and so you'll need to write it on the left as well, indicating that helium is properly a member of the S sublevel with its 2 electrons there. So write it there. So if you need additional time to fill out your periodic table, hit pause, make yours look like this one, and then as soon as you are all caught up, hit play, and we're going to get started helping you understand what all this energy level, sub-level stuff is all about. And welcome back. Okay, so now that you have a sense of the way the periodic table is put together, what does all of this stuff mean? Well, you may remember from class that we talked about the idea that electrons organize themselves around the nucleus of the atom. So if the nucleus is represented down here at the bottom of our diagram, these electrons organize themselves around the nucleus in ordered and repeated ways. So first of all, we understand that the energy levels range from 1 to 4. They actually go up to 7, but you're only accountable for the first 4 energy levels. Then from there, these energy levels are broken into what we call sublevels, and these sublevels are labeled S, P, D, and F, and then these sublevels are broken down into orbitals. Now, you may remember in class that these orbitals actually have unique shapes. The S's are spherical, the P's look like dumbbells and things like that. But that isn't really necessary for you to understand, because what we do is we represent the orbitals as boxes. So this one box actually represents the sphere of the 1s. This box represents the sphere of the 2s. And then these 3 boxes represent the 3 figure-8 or dumbbell-shaped orbitals from the P. Now, it isn't critical that you understand that, but we're hoping that by remembering some of this, you'll be able to link this to the orbital filling diagrams that we're about to go over momentarily. The important thing for you to understand is this order. you need to understand the order that these electrons fill. You need to understand that the first 2 electrons go in the 1s, then the next 2 electrons in the 2s, then the next 6 in the 2p, then the next 6 or 2 in the 3s, then the next 6 in the 3p, then the next 2 in the 4s, then the next 10 in the 3d, and it continues on from there. Now the problem is how are you going to remember that? So what we shared with you in class was the fact that the periodic table is actually set up like a map grid or the game Battleship. So if you can identify your position on a grid given a combination of numbers and letters, you can then figure out your way around a periodic table. So for example, this point right here is point 2C. We always identify this number first and letter second, so that number-letter combination is 2C because that's the intersection of those 2 points. This point here is the 3D as the intersection of 3 and D. Then this point would be 2B, and then the point in the upper left-hand corner, which is a little bit tricky, is the 1A. Using a similar pattern of numbers and letters, we can then find our way around the periodic table. Now, in order to do this, what we're going to do is we are going to count by atomic number. So we're going to go from element 1 to element 2 to element 3 to element 4 to 5 to 6 to 7 to 8 to 9 to 10, and we're going to count these elements in order by atomic number. Now, as we do, we are going through different sublevels on the periodic table that are identified by their number-letter combinations. So elements 1 and 2, hydrogen and helium, are in the 1s sublevel. Then elements 3 and 4 are in the 2s sublevel. From there, elements 5 through 10 are in the 2p sublevel, and it continues from there. Elements 11 and 12 are in the 3s. Elements 13 through 18 are in the 3p. Now when we move down to the 4th energy level, things get a little more interesting. Elements 19 and 20, as you might expect, are in the 4s sublevel. Now we've got to be careful with the next part of this. Elements 21 through 30 are in the D sublevel. We understand that, but we have to keep in mind that this is not the 4D, that this is the D minus 1. So 4 minus 1 makes this the 3D sublevel. So elements 21 through 30 are in a D, but it's D minus 1, making that the 3D sublevel. Then from there, we move down to elements 31 through 36, and the pattern returns. This is the 4p sublevel, and it goes on from there. This then is how we figure out the electron structures for these atoms. We find the element that we're trying to draw the structure for, and we locate the sublevel that it is in. So picking elements at random, if we were to look at element number 7, nitrogen, we know that that element is in the 2p sublevel because of its number-letter combination. If we take a look at an element like bromine, we understand that that is in the 4p because of its number-letter combination. If we look over here at something like rubidium, that would be in the 5s sublevel. And then looking in the D sublevel, if we were to look at an element like, for example, we'll say silver, silver is in a D, but this is not the 5D, it's D minus 1. So that would be the 4D sublevel. So using this ability to locate these elements based upon their number-letter combinations, we can now pull together what we call orbital filling diagrams. And when we do this, what we're going to do is we're going to locate the element, then we are going to build up to it, starting with the first 2 electrons in the 1s and building up from there. So if we look at our copy of the periodic table here, and if we want to know the order that these fill, we just need to count. So elements 1 and 2 are in the 1s. Then electrons 1 and 2 are in the 1s. Electrons 3 and 4 are in the 2s. Electrons 5 through 10, as we said, are in the 2p. Electrons 11 and 12 are in the 3s. Electrons 13 through 18 are in the 3p. Electrons 19 and 20 are in the 4s. Then electrons 21 through 30, as we've said several times, are in a d, but it's -1, so that would be the 3d. And then finally, for our purposes, out to the electrons 31 through 36, these are in the 4p. So that is then the order that we will use to write orbital filling diagrams. So now that we've got a sense of that, let's look at a couple examples given our periodic table, and then we're going to draw 3 specific examples. So the first one that we're going to do, as it says here on the left, we're going to do the orbital filling diagram for oxygen. So the first thing that we want to do is locate oxygen on the periodic table. And as we can see, oxygen is in the 2p sublevel. The problem is that we can't put electrons in the 2p without first filling the 1s and the 2s. So in order to work our way up to oxygen, we need to account for electrons 1 and 2, and electrons 1 and 2 are in the 1s. Then electrons 3 and 4 are in the 2s. Then, as we build up to electron 8 for oxygen, 5, 6, 7, and 8 are in the 2p. So now that we've got the order of sublevel filling laid out, we now need to figure out the orbitals where we will actually be placing these electrons. So in order to figure out the orbitals, we need to remember that we represent these orbitals with boxes, and that each one of these boxes can hold 2 electrons. So if that's the case, if we are looking at the 1, 2 electrons in the 1s, because there's 2 electrons in the 1s, we need 1 box. If we look at the 2s, there are also 2 electrons in the 2s, electrons 3 and 4, meaning that we need 1 box. Then when we look at the 6 electrons that are in the 2p, we understand that if there's 1, 2, 3, 4, 5, 6 electrons in the 2p, we're going to need 3 boxes in order to contain those 6 electrons. So now that we have our orbitals written down, represented by the boxes, it's now time for us to place electrons. Again, oxygen, element 8, has 8 electrons, so the first electron goes in the 1s. Notice that we draw it as an arrow, indicating the spin of the electron, in this case, spin up. Then when we place the second electron, we draw that as a downward pointing arrow, showing that these 2 electrons in an orbital have opposite spins. Then when we move along to electron number 3, that electron goes up in this 2s sublevel and orbital, and then the next electron is spinning down in the same orbital. Now we run into a little bit different rule. We still have 4 more electrons to place, electrons 5, 6, 7, and 8. These have got to be in the 2p. So electron 5 is the first electron in the 2p. Now we've got to be careful because electron 6 will not pair up with that electron. Because the 2p sublevel has more than 1 orbital, this electron will spread out because there's additional orbital space. So electron 6 will actually go unpaired in the next orbital, as will electron 7. Once we've placed electron 7, all of the orbitals in the 2p are now half full. So placing electron 8, it has no choice but pair up. We draw it as spinning down in that first orbital in the 2p, and this gives us the orbital filling diagram for oxygen. Now, in order to check ourselves to make sure that we're right, you'll notice that in oxygen we have 1, 2, empty spaces in oxygen. And if we look over in the 2p, we will see that oxygen is 1, 2 boxes short of the end of the 2p, meaning that those 2 empty spaces represent the 2 boxes that were short of the end, meaning that we did this one correctly. So now that we've done oxygen, let's move on and let's try one that has a charge. So now we're going to take a look at fluorine. But notice that the fluorine has a -1 charge. So in order to tackle this, the first thing that we've got to do is we've got to locate fluorine. And fluorine, like oxygen, is also in the 2p. So again, to build up to that, we need electrons 1 and 2, which are in the 1s. We need electrons 3 and 4, which are not there. Electrons 3 and 4, which are in the 2s. And then finally electrons 5, 6, 7, 8, and 9, which are in the 2p. Now again, we need the orbitals where the s's have 1 and the p's have 3. Now if you understood what we did previously for oxygen, I'll bet you understand what we're about to do for fluorine. So electrons 1 and 2 will be in the 1s, 1 up, 1 down. Electrons 3 and 4 will be in the 2s, 1 up, 1 down. Now for fluorine, we need 9 electrons. We've already got 4, so that gives us 5. 5 left to place. So electron 5 goes there. Now again, be careful with electron 6. It doesn't pair up, it goes unpaired. Electron 7 goes unpaired. Then electrons 8 and 9 pair up. That would give us the orbital filling diagram for fluorine. Now what we have to do is we have to account for the -1 charge. And if you remember from the second unit of the year, a -1 charge means that we are adding electrons. Doesn't mean subtract 1, it actually means a -1 charge. And if we remember that electrons are negative, that means that we've got to add an electron in order to give fluorine a -1 charge, and the only place that we can put that electron is there, and that gives fluorine a -1 charge. Now, as we talk about negative charges, maybe we can also talk for a second about positive charges. If we wanted to give this fluorine a positive charge, we would then be removing electrons. So if we wanted to go fluorine +1, we would take away the last electron that we placed, so that would be this one. If we wanted to go fluorine +2, we would take away its neighbor. If we wanted to go fluorine +3, we would pull out this guy. Fluorine +4 would remove this. Fluorine +5 would remove this. Now if we want to go fluorine +6, we actually can do that because we've got these electrons in the s, so that would be +6, and this would be +7, removing that last s electron. Now, if we wanted to go fluorine +8, we cannot do that. The idea is that we can only add or remove electrons from the highest S and P. And because our highest S and P is in the second energy level, the first energy level is off limits, and we cannot add or remove electrons from that energy level. All right, so now we've looked at fluorine and we've looked at ions. Now what we need to do is we need to look at a transition metal. And so we're going to look at copper, which is in the D sublevel. But remembering what we learned before, this is not the 4D sublevel. This is D-1, so this is in the 3D. Now, we're going to run into a little bit of problems here because I don't have space to write this all the way out in this limited space. So I'm going to write this up here so that we have room to spread this out. So we understand that we're building down to the 3D sublevel. But again, we've got to start with electrons 1 and 2, which are in the 1s. Then after that, electrons 3 and 4 are in the 2s. Electrons 5 through 10 are in the 2p. Electrons 11 and 12 are in the 3s. Electrons 13 through 18 are in the 3p. Electrons 19 and 20 are in the 4s. And then finally, electrons 21 through 29 are in the d, but remember that it's the 3d. So now again, we need orbitals. We remember that the s the S, and the S all have one orbital. We remember that the P has 1, 2, 3, 4, 5, 6 electrons, which requires 3 boxes. And now we got to talk about the Ds, because the D shell has 10 electrons in it. So if the D shell has 10 electrons, that means that we need 5 boxes, which I hope I can get to fit there. Okay, so now that we've got our 5 boxes for the D, we now need to place our electrons. And if we look on our periodic table, copper has 29 electrons. We've got to spread them out in the boxes. So the pattern is just like it was for oxygen and fluorine. 1 goes there, 2 pairs up, 3 goes here, 4 pairs up, 5, 6, and 7 go unpaired, 8, 9, and 10 pair up, 11 and then 12 pair up, then 13, 14, 15 go unpaired, 16, 17, 18 pair up, 19 and 20 go in the 4s. So that takes us through electron 20. We still need to get to 29. So we're going to go 21, and then just like in the P's, these will go unpaired. 22, 23, 24, 25, 26, 27, 28, and 29. So what we've created then is the orbital filling diagram for copper. We notice that there's 1 empty box between copper and the end of the sublevel. We notice that we've got 1 empty space in the 3D, making us believe that we've done this properly. Now what we have to do is we have to account for the +1 charge. Now, if you were paying attention as we were talking about fluorine, you may remember that we said that we can only add or remove electrons from the highest S or P. And as we look at our orbital filling diagram for copper, we need to find our highest S or P sublevel, or and P, and that would be this. The highest level that we have is 4. And the minute we identify the highest level is 4, that means we cannot add or remove electrons from anywhere else. So if we want to give copper a +1 charge, we need to remove 1 electron. But we do not take that electron from the D. We don't cross it out, but we do not take electrons from the D because that is not S or P and it's not highest. So the electron that we will remove in order to give copper a +1 charge is actually this electron in the S. We would erase that. Let's see if I can get it to erase. We will erase that electron, removing that from the 4s, and that would give copper a +1 charge. So there you have it. We have a sense of how to do orbital filling diagrams. We understand the order that the sublevels fill. We now know how to represent electrons as arrows and how to handle this not only for neutral atoms but also for ions. We're now going to move along and we're going to shift gears and talk about Lewis dot structures. Lewis dot structures or Lewis dot diagrams are much simpler than orbital filling diagrams. When we do Lewis dot diagrams, the only electrons that we are representing are what we call the valence electrons. These are the very same highest S and P electrons that we just talked about adding or removing when we form ions. So when we do Lewis dot diagrams, all that we are representing are the valence electrons, and again, these are in the S and P. So if these electrons are in the S and P, we need to remind ourselves how these electrons fill these orbitals, just like we did a moment ago with orbital filling diagrams. So we remember that the first electron goes in the S. Then when we place our second electron, that one goes down in the S sublevel, filling that sublevel. Then if you remember carefully, the next 3 electrons, 3, 4, and 5, go in the P sublevel, but they go unpaired because they have rooms to spread out. Then 6, 7, and 8 pair up, filling that sublevel. So what we're going to do in Lewis dot diagrams is we're going to represent these same electrons, these valence electrons, but instead of drawing them as arrows, we are going to draw them as dots. And those dots will separate or will surround the abbreviation of the element. So there is not an element XX, but as an example, the way that this will work is we are going to imagine that there is a box above the abbreviation. That box represents the one orbital in the S sublevel. Then left, bottom, and right, we are imagining that there are 3 boxes, and these 3 boxes represent the 3 orbitals in the P sublevel. Now, instead of drawing arrows in these boxes, we are going to draw dots. But we don't actually draw the boxes. So we're going to fade these boxes out, understanding that we still imagine them to be there. So then as we place these electrons 1 and 2 are paired up together for the same reason that these electrons are paired up together. Now remember how we placed the next 3 electrons. 3, 4, and 5 went unpaired because they're spreading out in the P's. Well, similarly, 3, 4, and 5 are going unpaired because they're spreading out in the P's. Then we came back and filled the boxes 6, 7, and 8 as we had to pair up. Similarly, here we have 6, 7, and 8. So we understand then that the electrons place like this. 1 goes here, 2 pairs up. Then 3, 4, and 5 go unpaired. Then 6, 7, and 8 pair up. So if we can remember the pattern to how these dots place, then all we've got to do is figure out how many dots are in the diagrams. But to do that, as you might guess, we go to the periodic table. And the number of dots for an element is actually given by the group that they are in. So all of the elements in the first group will have 1 dot. All of the elements that are in the second group will have 2 dots. Now we need to talk about the D's and the F's. So how many dots do these have? Well, remember that the only valence electrons are the S's and the P's. So the D's and the F's are never valence electrons. But in order to get into the D shell, we had to go through the S shell that leads up to that. So what that means is that all of the D's and all of the F's will all have 2 dots, those 2 dots being the 2 electrons in the S sublevel. Then after that, we move back out to the P. These P electrons are valence electrons, so we have 3 valence electrons, 4, 5, 6, 7, and finally 8 valence electrons. So if we merely count the group, we can figure out how many electrons they have. These have 1, these have 2. All of these have 2, these have 3, 4, 5, 6, 7, and 8 electrons. So keeping that in mind, let's jump over here and let's look at some examples. So these are the ones that we're going to do. So first of all, magnesium. It's important that we first write down the abbreviation of the element. Now that we've got the abbreviation of the element, we find magnesium on the periodic table, and it is in the second group. Because it's in the second group, that means that it's got 2 dots, and we need to remember that those 2 dots are paired up because those 2 dots are in the S sublevel. They're paired up. Now we look at gallium. Gallium is element number 31. It is in the first, second, third column. It's in the third group. That means that it's got 3 dots. But remembering the way that we place these dots, the first 2 have got to be paired up because those are the electrons in the S. Then this third electron, this P electron, will be unpaired in the P. So the electron dot diagram for gallium looks something like that. Now to do the next three, I'm going to clean up my mess. So if we take a look at iodine, iodine is element number 53. We need to count over to its group. So we go 1, 2, 3, 4, 5, 6, 7. So we understand that iodine will have 7 valence electrons. So we go iodine is the abbreviation. Remember 1 and 2 pair up, then 3, 4, 5, 6, 7. Remember that 3, 4, and 5 go unpaired, then 6 and 7 pair up. But now we need to account for the fact that this has got a -1 charge. Again, to give it a negative charge, we add electrons, and in this case, we're adding 1 electron, so that would be the Lewis dot diagram for iodine. Cleaning up our mess again, we're now ready to do selenium. Selenium, counting over, is in the 1, 2, 3, 4, 5, 6th group on the periodic table. So we understand that selenium will have 6 dots. 1 and 2 pair up, then 3, 4, and 5 go unpaired, and then electron number 6 is forced to pair up in the P sublevel, and it looks like so. Now what we need to do is we need to give this thing a +1 charge. So to give selenium a +1 charge, we need to remove an electron. But the electron that we remove has got to be the last electron that we placed. And if you remember, we placed these electrons 1, 2, 3, 4, 5, 6. So the last electron, the first electron to come out is the last one that was placed, and that would be this guy. So this electron gets removed in giving selenium a +1 charge. Now finally, calcium. So calcium, cleaning up my mess, and looking at calcium, calcium is here in the 4s sublevel. It is in group 1, 2. That tells us that calcium will have 2 dots, and we keep in mind that those 2 dots are paired because they're in the s sublevel. But now we need to account for the +2 charge of calcium. And this is interesting because we see that calcium only has 2 valence electrons. Because it's only got 2 valence electrons, to give it a +2 charge, we take both of those electrons away, so we draw calcium without any valence electrons. So this would be the Lewis dot structure for calcium with a +2 charge. Notice, however, when we did all of these ions, we did not include charges in the Lewis dot structure. So this would be the Lewis dot structure for calcium +2. Doing this would be incorrect because we do not include charges in our Lewis dot structures. So there you have it. We've gone over the periodic table. We've talked about the way that it's organized into energy levels and sublevels. Then we looked at the orbital filling patterns that start at the nucleus and build out through the 1s, the 2s, and the 2p. Then we realized that that exact same pattern is on our periodic tables as we read across our periodic tables: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. Then using those understandings and drawing boxes as orbitals, we learned to draw orbital filling diagrams. Then by focusing on only the valence s and p electrons, we took that idea and learned to draw Lewis dot structures, drawing the dots using the same pattern that we used to fill the s's and the p's. So now that we've gone over all of those things, your next task is to go back and do the assignment that you printed that has 5 examples of both Lewis dot and orbital filling diagrams. Once you have done those, if you're in Miss Call's class, you will be joining her for a Pride review session on Thursday. In order to get into the review session, you've got to bring your notes. You've got your notes from this video, your periodic tables, and that assignment completed. You've got to bring those 3 things, and you've got to be there by noon. If you don't bring those things, or if you're not there by noon, you will not be allowed to interrupt the group, and you will lose the opportunity to do the remediation. Once you have pulled this all together, then on Thursday you'll join Miss Call, or if you're in Mr. Knappenberger's class, you will come to Pride on Friday. And during those Pride sessions, again, Thursday with Call or Friday with Knappenberger, we will do additional teaching, we'll answer questions, and you will have a larger review assignment that you will then have the opportunity to complete. Once you have done that assignment and checked your answers for that, you will then have the opportunity to take a replacement test on Monday. That test will only be offered Monday after school at 1:30. You must be there, obviously, in order to take this test. And in order to be able to get in to take the test, you must have completed the assignment that you're going to be given during your Pride session. Once you have successfully done that, you come, you take the test, and we are looking for you to get 80% or better on the replacement test. And the replacement test only covers orbital filling and Lewis dot structures. If you get better than 80% on that replacement test, regardless of what you got on the first test, your score will be changed to a 75%. So thank you for getting involved in the remediation process. Please understand that you're always welcome to ask additional questions if you need, but for now, take a look at that practice assignment, and we look forward to seeing you at Pride on Thursday with Call or Friday with Knappenberger.